Welcome to UniCourse. This is a Unit 31 electrical distribution system. We're going to be looking at the hints and tips of assignment 1. I'm going to take you through the theory behind electrical distribution systems, and then at the end we'll be looking at the hints and the tips on how to complete this first assignment. So we'll look at the features of electrical distribution systems. Reviewing the component symbols, they can be found in the UniCourse guide notes and also in further reading. We'll look at different methods of single and three-phase connection. We'll summarize methods used of safe fault finding, and then we'll look at electrical distribution systems. So what we've got here is an overview of the actual assignment. As you can see here, the first pass is about the electrical distribution using research information, which is included in the UniCourse guide notes and further reading, how electricity is distributed through the UK. What we've also got as well is on P2, you're looking at the components. As I mentioned, they can be found in the UniCourse guide notes. What I recommend you do with that is you hand sketch those symbols. The next question, you were looking at different methods of single and three-phase connection, and that UniCourse guide notes and further reading to explain it. What's important you make sure is that you annotate all the diagrams. And the first of the higher questions in the merit, you'll summarize methods of safe fault finding, and that we include in using photographs and diagrams, and explain how you would fault find within the electrical distribution industry. And then finally is just to look at the electrical distribution again, which will include further reading and make some more observations and comments to complete that assignment if you're going for the higher grade. Now here on our right, this is a typical electrical power station, but what we see here is on the left, see this tunnel here, but now we don't have coal-fired, we have one or two oil-fired, a lot of the nuclear power stations, but the diagram generally shows how power is distributed in the UK. And what you'll notice is that the power is generated at this point here. Then we have a step-up generator, which then takes it from a certain voltage up to around about 400 kV, 400,000 volts. And that is then distributed around the UK. Quite often not is they're on pylons, but in areas where they can't put a pylon, they have to do it underground, and that can go under fields, and they have to get permission of farmers and things like that. And usually it's mainly what we see here from the national grid, these pylons, and then it's dropped down, and then it goes along again to a certain area, and eventually dropping down again to 11 kV after it's been at 400 kV down to 33, and then we get it dropping down even further to where we're at the 240 volts, and then we have 110 depending if it's for the residential, domestic, or light industry or heavy industry. So that is a picture which is important for you to have a review it. If you're using anything like this in your assignment, you must annotate it and put your own words around it. Fuels today, coal is no longer the main fact. In fact, coal is actually being phased out in the UK. Nuclear is used a lot, and gas and oil. We also have the hydroelectricity, biomass, and wind or solar. And these are becoming more popular now. We're looking at a cleaner type of energy. So these what we use to power the turbines, and they are dotted around the UK. And what I think ideally is are looking for fewer power stations especially if they're going to be using things like the nuclear, which is gathering at the moment. These turbines quite often will generate around about 33 kilovolts, and that is a reason why we have to then step them up, because they're stepping up because the fact is that there will be a volt drop onto these lines, and then when they eventually get back down to the transformer, even so we've still got high voltage. You imagine every household or a factory, each one's a load, so we have to stabilize the voltage, and that's why in some cases when there is a football game on or some form of concert on live TV, they will bring in backup power stations so that they keep that the electrical energy is all stable and there's not a dip. So when we talk about three-phase and single-phase, what you'll find that if you're in a certain neighborhood, and this has happened to us, where the lights or the power in your house goes down, but across the road it's on, and what happens is that you have different phases, and we use three-phase. That is quite common. Well, it is common today, and that can be then distributed around for local industry, and it also used for the domestic market as well. These cables are made of steel, and you'll see these around the place quite often in the countryside. We have these around about 400 kV, and then they are stepped down to about 132. Now that's quite big voltages, but they don't yet come down where they're set down to about 33,000 volts. And then we're getting down to near manageable voltage, which is around about 11 kV, 11,000 volts. And that will then go to the local substations, which are all, you'll see, usually you'll see some form of fencing around it, you'll see some bushes and trees, and then you'll see a little sign say hazardous area, do not go inside, and it's only by the national grid who are able to gain entry to it. So we've got this here. Now you'll see the star and the Y arrangements, that's the American terminology for the actual delta. Y is we use that, which is one other version for the three-phase. So here we have a typical here of the pylons. And if you're a bit like me, you've been taking photographs, you'll see that the way they're set out, they're very high up. In fact, the ones local to us do actually go quite near a river, and there is a sign saying, please do not do any fishing near us, because if you've got your fishing line anywhere near that, you know, you could get electric shock. Even so, the line is not made out of any conductor, but if you've got it where it's been in the water, it will conduct. And sometimes you can actually hear the crackling noises from these pylons. So they're very, very high voltages. Now here we have a sort of pictorial view again of it. We see the transformer, and we can see how it's distributed around. And we've also got now using wind farms as well, and how the voltage is distributed around the UK. And what happens with the national grid, they will have a control room centralized in the UK, maybe one or two which are, well, will be around in the local areas, and they will be monitoring the actual supply voltage and what the consumer is using. Usually it's more for the consumer side, is usually in the evenings, where we've got the kettles boiling and other pieces of kit going on. But in today, where a lot of homes now are using low voltage lighting, and they're using washing machines and dryers, which are more efficient, and the power consumption is not too bad. But years ago, we used to see quite often a flicker of what was happening in the national grid. We're switching over to or other power stations where they can cope with a load. Now, the engineer would be looking at this as an overview, and quite often noise, they will be now on special software and diagrams set out by the national grid, and they can see where there's any issues, and they're probably highlighted on their screens. Now we're moving on to the single phase connections. This is normally will be only for household. 3-phase is on the things like where you have the industry, light industry, heavy industry, and some of the church halls. If there's a massive campus there, they may have it where they may have 3-phase. The university, colleges, and the schools will probably be on a 3-phase, and different parts of the camp, depending on the size of it. If it's a very small village school, that probably still be on single phase. Well, this is mainly for the domestic side. So here we see single phase versus 3-phase. Now in America it's slightly different, but we're not worried about that. Now, this is what we have with the 3-phase. It allows for the peaks and dips. The single phase that doesn't offer that, but generally speaking, we usually get at the end within the house around about 230, 240 volts, as long as it doesn't drop down below 210. Otherwise, a lot of the appliances won't operate. Of course, with the 3-phase power supply, that has a more constant. Now, this is very important. Industry where they've got big production lines, they may have machinery which needs to work on special voltages. They can actually use other pieces of kit to stabilize the voltage, but more often than not, 3-phase is generally a lot more stabilized, and it's probably more efficient as well to run. So for industry, they don't want to be wasting energy, so they will go for the 3-phase. Also, it also transmits 3 times as much power, which makes it more efficient as well than the actual single phase. So therefore, 3-phase power supplies more efficient, 3 wires or 4, that is including the earthing conductor. Now, what you also need to do is, this is a hint and tips regarding the actual assignment. Now, we may say, why do we get a thing called star and delta? Well, the way I always look at it is, if you look at the delta connection, you can see the way the coils, that is a Greek symbol for a delta. So that's always a delta connection. And the top one, as you can see here, is set out like a star. Now, in America, they would call that the Y connection, because if you turn it upside down, it looked like a Y, W-H-E-Y. But here in the UK, we call that the star connection, and we call that delta connection. And on the left-hand side, we can see how that is set out. Now, you don't really, unless you can see how at that point there is a center for the neutral, and here you can just about make out like a star, but on the delta one, it's a bit more difficult. You can see it a lot easier here, but you can see how if you follow the wiring through and you follow it through on the delta side, they're exactly the same. So what we have here, the bottom one here is delta connection, star connection. Bit of a hint, if you're doing your assignment, don't forget, it would be better if you do a sketch of it and annotate it. If you are going to cut and paste, make sure you put your own annotations onto it. Now, one of the areas which is very important in the electrical distribution is fault finding. Now, I'll give you a scenario which when I met with some of the National Grid engineers some years ago, and they were telling me what was happening. There was an area down, I think it was in Wales. It was a stormy night. There was electrical storm. One of the National Grid pylons had fallen over. It got hit by lightning, and they had to go down and do some repairs on it. But there was other issues around it all. So, of course, the fault finding, they have to use very much safe fault finding. You can't just go there with a box standard multimeter because the voltages are very high. See, these guys, which are known as jointers, they are well experienced, trained up to be able to work on very, very high voltages. Some of the techniques we look at are basically techniques we use in a lot of electronic industries. Is actually looking at the input and outputs. what you need to find out is there a voltage at the input to a certain point of it. So if it was on a pylon, it would be what voltage is coming from the other pylon to the one that's faulty, or if it's to a step down transformer, what voltage would be coming at the input of the primary of the transformer, what goes on the secondary. And that is quite commonly the transformers on these sometimes will fall over, they will fail, and therefore they have to put a temporary transformer in until it's repaired. So they have to systematically, and that's important because of the safety aspect of it. You can't just hazardly work on these. They have to carefully check each section to see where the supply is and where the supply is not there. And then from there, they can then deduce where the fault is. And then they have to make decisions. Can they actually do a temporary repair? Can they repair it so it's permanent? Or will it require taking out? And then they need to have a standby or sort of have the distribution moved somewhere else, which gets very complicated. Now, the half split method, which is used right across the electrical and electronic industry, this is where you've got, for example, A, B, and C, and A is the input, and the C is the output, and they normally go to B. So we could be looking at things like transformer, the cable connectors, fuse, substations, MCB, anything. But what you need to do is determine what the input voltage is and make sure there's input voltage at that point. And then you know there is a fault somewhere between where it goes onto the input to where it comes on at the output. So they use special equipment for that. We were looking at one or two photographs, some of the kit they actually use. So the midway point is always a good point to start. So here we've got an instrument used. Now this would not be used on anything on the 1000 volts. You wouldn't use it on 32 kV. These quite often are not. I can see from the installation would probably be used either 110, 240 on domestic voltage, possibly up to 1000 volts. It depends what this meter can withstand. And you can see here, all the leads are well and truly insulated. And even with the insulation, the engineer who's using it will also have to wear protective gloves as well, just as a secondary precaution. So this is a modern insulation tester, and this will be checking the insulation between ground, the live, and the neutral on Earth. Now we look at this photograph, and one thing I notice is, look at the PPE he's wearing here. He's working on some very high voltages. The gloves he is wearing, and then they've got this meter here. Now it's not your box standing multimeter, and you can see all the leads coming out of it. And probably got a screen over here, and it's probably making, it's actually giving the engineer some waveforms and various statistical information to say what is happening with the power at that point in the system. So if you are working on very high voltages, like this person is, they have to wear specialized gloves and also wearing this type of clothing as well for the protection. And here is another engineer. It's probably something similar, yet again wearing protective equipment, and there he's got all his leads connected up there, and then probably a bit of software in there which allows them to do some working out what the voltage are, what the power is, and what the current is. And this in the case is looking at the power quality, and is looking at the energy analyzing. Both can be used for single and three phase. So they can connect these up, and then they use the meter to decide what he wants to look at. Now, at first sight, this diagram looks quite complicated, but the engineers working on the national grid will be quite familiar with it. And this gives you an overview. And if they're looking at the system across an area, they may want to just look at certain sections. before they actually get down to an individual area that they need to test. So this is just showing a snapshot of what's going on out of the national grid. And here's a more simplified view as well. We've got the three-phase, we've got the earthen conductor, and the engineer would look and decide, what stage they need to work at it, and maybe just changing some of the pylons, and moving it, or they're bringing in another transformer into a local area. And quite often, if there's a neighbourhood where there's some new estate building, and then they need to have a new substation built, and they were looking at things and very much an overview of it, instead of actually down to the smaller area of the component and down to the local household. Yet again, we have an overview photograph of the power distribution of the national grid, and it just gives you an indication how it's set out. And this is just only an overview. If you go to each section, there'll be a lot more wiring. We can see here the pylons and the connections here, and how it's all distributed around it. Now, in the last probably 10, 15 years, where before that, electricity would only be generated at the power stations, where they were traditionally coal, then they went over to oil. Of course, you've got the nuclear power stations, but also now we have the wind farms, which are dotted up around the country. If you go around the Oldham area, you'll see quite a few of them. Or you go into the Midlands and parts of Daventry around there, you'll see a lot of these farms of these wind farms. And also we've got solar energy as well. So it's not just purely energy developed from the power stations anymore. It can come from anywhere. So this is an overview. Okay, so we more or less run halfway through it. What I want to concentrate on now is completing the assignment. Don't forget is your diagrams will need to be annotated. Your text, if you've got sections from somewhere else, that needs to be referenced, citations, and a bibliography at the foot or the end of your assignment report. So let's discuss one or two areas. So describe how electricity is distributed from the power stations. Use a diagram, and of course you can find them through the internet, or you have a comprehensive one in the UniCourse guide notes, but please make sure you annotate it with your own explanation. The 5 symbols, yes, you can find that in the UniCourse guide notes. Further reading, what I think is important is that you hand draw each of the symbols and explain what they actually are. 3-phase, yes, again, this needs diagrams, explanation how they are, anything that you've actually acquired from either the UniCourse or from further reading, that needs to be annotated as well. The safe fault finding, that is for the higher grade, and that includes using the workbook. Now, this is an important one. I find a lot of students have been completing this question, but they've been using a lot of text, but they're not including diagrams, schematics, and or photograph evidence. I like to see that if you complete this question, you include what I've just said, photographs or diagrams and sketches to go with it. Then the final question is, you'll be looking at what is in the electricity distribution. Now, students have said to me, so what do I write about? What you do is you're developing what you've written for task 1, for task A, and you are expanding on it, including further reading. The UniCourse guidebooks will help you through a lot of the assignment, but as I say, you need to include some further reading. Students, for some reason, don't read the assignment question properly, so they go off at a tangent. Make sure you read it carefully. Draft out your evidence first. Make a note where you found the information, because that will be important for your bibliography for when you're referencing it. The Harvard referencing is what I recommend, what we stated as well through the guides for the UniCourse, and that needs to be included, putting some citations in each of your photographs or any written information which is not yours, and of course you need to reference it formally at the end of the assignment. Ideally, you need to rewrite the text that you found from any web pages. Of course, I keep saying, annotate all your diagram, sketches, and photographs. A lot of the resources you'll find in the UniCourse Moodle. Okay, this is just showing Unit 21, but you look for Unit 31 and you'll find the specifications, the handbook, assignment, and also you'll find the live recording classes. Go on to it. So we're up to the first one for this season. There's 4 together, and usually around about 10 days, the first class is usually uploaded, depending on time. As I said, further reading is strongly recommended. You find a lot of information just by Googling it, but what is important is that you don't cut and paste it, you reword it. Any diagrams you use, that needs to be referenced and annotated with your own words. And this is just an example from another unit where you can see here a lot of diagrams, a lot of text, but you need to rewrite your text. Diagrams need to be put into paint, take off the labels, and you just re-annotate it yourself. And here's a nice one, just showing you just from another assignment where we've got the annotations on it, which is clearly marked out. I like stuff like this. The arrows pointing to what is. And this is the Harvard referencing. This is telling you the names, the dates, and where it's found on the internet. So just wanted to bring up this. This is now the new format of the assignment. What is important, especially for Unit 31, where there's a lot of research evidence, it needs to be typed up. The diagrams, any diagrams that you're willing to put into it can be annotated. And I do recommend for this assignment for Task B, draw and describe 5 symbols. I'd rather see that one hand sketch and then just typed up the annotations. And it gives you also an idea of the word count as well, which is what we're looking for. Right, that is the end of this presentation for Unit 31. And have you got any questions? Thank